Assalamualaikum warahmatullahi wabarakatuh. So today group 1 are going to present about the torsion of bar. So for the introduction, torsion happen when a bar or shaft is twisted by a force that called torque. So these are the example of torsion in a real life. So first we have vehicle drive shaft. Second we have a screwdriver. Third, turbine shaft. And fourth is a bicycle crank. So torsion produces shear stress and causes the bar to twist along its axis. And then the amount of twisting depends on the applied torque, bar length, material, and cross-sectional shape. We need to understand the torsion because it's important to ensure the components can cooperate safely and efficiently. Okay, the objective for the experiment is first to investigate the relationship between applied torque and angle of twist for different type of bar. Second, to determine the modulus of rigidity G of different material under torsional loading. And then for the scope, for the experiment is limited to 3 types only, which is aluminium, copper, and steel. And then the radius of the pulley used in the experiment is fit at 150 mm, and the root length used are limited to 200 mm and 400 mm. And lastly, the applied loads are only from 5 Newton to 25 Newton.
For our theoretical part, the experiment is based on the linear distribution for the shear strain produced in the material. So the shear strain is not uniform in the cylinder bar, and it is zero at the longitude axis, which is center, and it linear increasing to it until its maximum value at the outer radius is called the row of the bar. So when the bar is undergo torsion, which is T, is due to the twisting moment applied along its axis. So the resulting shear strain operating in the direction particular to the road reduced at any given location in the cross section. So for our torsion, what's a torsion? Torsion is the force applied at the two ends of the bar. And its formula is the rho times F times sine theta. So what is the angle of twist? The angle of twist is the rotation displacement for a torque T is applied to the shaft fixed one end, and it creates an internal shear strain that causes the cross-section to rotate relative to each other. So given the angle of twist is the phi equal to a T times L over Jg. So for phi it's the angle of twist with the radians as a unit, and T is called tau, which ends as a unit, and J is the polar moment of inertia. The unit is n, and the L is the length of a cylinder bar with the meter as a unit, and G is the shear modulus of the bar materials. The unit is Pascal. So for shear modulus G and the polar moment of inertia J, it's the ratio of the shear stress to the shear strain, and the polar moment of inertia is the measure the resistance to a torsion. So the polar moment of inertia J, the equation is the pi times d power 4 over 32, where d is the diameter of the bar. So based for our reference, the theoretical value of shear modulus for aluminum is the 28 gigapascal, and for the copper it's the 45 gigapascal, and for the steel it's the 75 gigapascal.
So for the experiment setup, this one is the figure 3 that show the whole experiment setup. So in this figure, we will show that there are the small pulleys, the cables, the 3-joint direction with the big pulley at the ends, the fronts, the copper bars, the 3-joint direction, and the rotation screw. So for the apparatus and the material that we use the aluminum bars, the copper bars, and the steel bar. And we also use the ruler, digital calipers, the drill chart key, the lock, the weight hanger. So for the methodologies, the first step is the diameter of the copper, aluminum, and the steel solid bar was measured by using a digital caliper, and the diameter of each bar was recorded. The second step is the copper solid bar was paired in the positions, and the drill chart was locked by using a three-jaw chart key to measure the bar help tightly to prevent the movement. So third step is the relation scale was and the pointer was set 200 millimeter from the fixed clearance by using the rulers. And the fourth step is the pointer was aligned with the zero mark before applying the lock. The fifth step is the hands the lock angles with the 5 newtons lock at the end of the lock. So the step 6 is the angle of the twice of the specimen was recorded in the table 1. And the step 7 was the step 4 to step 6 was repeated with the lock weight increments for 5 newtons until the total lock for the 35 newtons was pressed on the lock angle. And the step 8 was the lock angle was removed and the rotation scale and the pointer was changed to the 400 millimeter from the clamp. So the step 9 is the step 4 to the step 8 were repeated for the 400 millimeter length of the rotation scale and the pointer. So step 10 is we record the theta in the table 1. And the step 11 is the step 4 to the step 10 will repeat by replacing the copper solid rod with aluminum solid bar and the steel solid bar. And the step 12 is we calculate the top of the each solid bar with the different angle of the twice. So after that we record for the step 13 we plot the graph with the angle of the twice against the top. And the step 14 is we calculate the polar moment inertia with the J by using the equation 1. And the equation 1 is shown in the theory. So the step 15 is we obtain the slope from the graph with different distance and the slope was equal to the gradient of the graph. So the step 16 is we calculate the shear modulus with the G, and we use the equation 2 and that shown in the theory and to calculate the percentage error for the shear modulus G between the estimated value for the each solid bar.
So the next part is the result and discussion. So here we have the table 1, which is data of diameter, torque and angle of twist for aluminum solid bar. Here we have the average diameter for the aluminum solid bar is 6.2 mm. Next is we took the angle of twist for 200 and 400 mm different rotation, scale and pointer from the fixed clamp. And next, we will be counting the torque at 200 mm twist and 400 mm twist using the formula T equals to RF, where R is 6.2 over 2, which is 3.1 mm, divided with F, which is 5 Newton. And so we'll be getting 15.5 torque for both 200 mm and 400 mm twist. Next, this is the table 2, which is the table for data copper solid bar, and this is table 3 for data steel solid bar. So next, draw the graph of angle of twist in radian unit against torque in nmm unit. So this is all 6 graphs for all 6 data that we have. Okay, so moving on to the first question of discussion is, to what extent does the experiment verify the torque twist formula based on the graph plotted? So based on the theory of the experiment, where the formula for angle of twist is TL over JG, from the graph of angle of twist, we can modify the equation by the mathematical method, which is y equals to mx plus c, and y equivalent to angle of twist, x equivalent to t torque, and we know that the slope of the graph m is L over jg. So based on the graph plotted, it is known that although the calculation has the same shape of graph compared with the theory, it does have different value of equation, where the value for gradient and y-intercept will be different. Also, although it shares the same formula, the value of the gradient is affected by the length of shaft and also the diameter of the shaft. As in this experiment, the value calculated is only 400 mm and 200 mm. As a result, the experimental value may differ with the theoretical value. So as the sample of calculation is, the first one is the aluminium. For the length of shaft 200 mm, we get a linear equation y equals to 0.011x plus 0.3 to the power of 10 negative 5, where m is the 0.011. And the polar moment of inertia J, we calculate the polar moment of inertia J pi times with diameter over 2 to the power of 4 over with 2. So pi times with 6.2 over 2 to the power of 4 divided with 2, and we will get J 145.06 mm to the power of 4. So we calculate G next using the same data, which is G equals to L over JM, where L is 200 and J is 145.06 and M is 0.011. So we get the G is 1 to 5.34 Newton per millimeter square. So after calculated all the other materials and lengths, here is the table 4, which is table of data for shear rigidity of modulus G values. with where I summarizes all the other calculations, and we can gain G average G bar from the calculations. Okay, so for the second question is the comparison between three different types of bar with different length of rotation scale and pointer from the fixed clamp. So based on table 1, 2 and table 3, the steel bar shows the smallest angle of twist at 200 mm, indicating that it has the highest resistance to torsion. The aluminium bar shows a moderate increase in angle of twist as the load increases, while the copper bar shows the largest angle of twist under the same load. At 400 mm, all three bars show increasing angle of twist as the load increases. This proves that the angle of twist is directly proportional to the applied torque. Among the three materials, copper twists the most, followed by aluminium, while steel twists the least. Therefore, the rigidity of the materials increases from copper, aluminium, and finally with steel having the highest modulus of rigidity. So the third question is based on your findings. Explain the relationship between the modulus of rigidity of materials with the parameters such as types of materials for the bar, length of the bar, shape of the bar, and polar moment of inertia. From the results, it is clear that the modulus of rigidity G depends on the type of material. A higher G means the material is stiffer and more resistant to shear deformation, while a lower G means it more flexible and deforms more easily under load. In this experiment, steel shows the highest rigidity, followed by aluminium, while copper shows the lowest. This is because steel has a stronger internal structure that resists twisting, while copper deforms more easily under the same load. The shape of the bar also affects torsional resistance. A solid circular bar provides better resistance to twisting compared to other shapes because the shear stress is distributed more evenly across the cross-section. The relationship between parameters is given by Z equals to TL over J, angle of twist. According to the equations, when the length of the bar increases, the value of G obtained will increase. As the value of the polar moment of inertia increases, the value of G obtained will decrease. This indicates that if the dimension of the bar increase, the value of G will increase, in which the bar will be more resistant towards shear deformation.
Further conclusion. In conclusion, the objective of these experiments, which were to investigate the relationship between the applied torque T and the angle of twist for different types of bars, as well as to determine the modulus of rigidity G of different materials under torsional loading, were successfully achieved. The results show that the angle of twist is directly proportional to the applied torque, as demonstrated by the graph plotted from the experimental data. As the applied torque increases, the angle of twist of the circular cross-section specimens also increases. Furthermore, the modulus of rigidity G for each material was determined from the experiment, yielding values of 2360.57 Newton per millimeter squared for the aluminium bar, 2086.25 Newton per millimeter square for the copper bar, and 3219.13 Newton per millimeter square for the steel bar. Furthermore, the differences in the modulus of rigidity obtained for each material show that each material has a different resistance to torsional deformation. Based on the experimental results, the steel bar recorded the highest modulus of rigidity, followed by the aluminium and copper bars. This indicates that steel has a greater ability to resist twisting when torque is applied, while copper is more easily deformed under the same loading condition. The results also show that materials with lower rigidity tend to produce a larger angle of twist. Therefore, this experiment successfully demonstrated the effect of material properties on the torsional behavior of circular shaft and their response to applied torque. As for the safety procedures, the first one is to wear appropriate closed-toe shoes or safety shoes to protect the feet from falling objects or equipment. Number 2 is make sure the torsion testing machine is in good condition to avoid equipment damage or malfunction during the experiment. Number 3 is do not touch the rotating parts while the machine is operating to prevent hand injuries. Next is to make sure the bar is firmly clamped at both ends using the 3 jaw chucks to ensure it is securely held, as any loose clamping may cause movement and affect the accuracy of the readings. And then observe the torque and angle of twist readings carefully to avoid incorrect data collection and experimental errors. If any abnormal noise, strong vibration, or malfunction is detected, immediately stop the experiment to avoid equipment damage or potential injury.